visiting amarpathshala.com. Hope you all had a wonderful time in it with your friends and family. I know I did. So now guys, since the festivities are all over, it's time to come back to study and work. As you can see, in today's lecture, we are going to discuss about the atomic structure and the periodic table. And this is part 2. In part 1, which was titled Introduction to Atomic Theory, we learned about how atom was discovered, how the word atom was coined, and by whom. And we also learned about the different theories of atom and the history behind those theories. In this chapter, however, we discuss in more invasive detail about the structure of an atom and etc. So, without wasting any more time, let's begin. So guys, if you concentrate on the diagram right in front of you, you can see that this is a simplified structure of an atom. In the center, you have the nucleus. Now, as we know from our previous part, that the nucleus is where the protons and the neutrons are situated. So as you can see in this diagram, the nucleus is where the positively charged protons and the zero charged neutrons are there. And above the nucleus, orbiting, are the negatively charged neutrons. And then if you shift your focus into this table, you can see that these are the particles in an atom, and you can see the relative mass and the relative charge of each of these particles. See, the proton, which is, as we know, resides in the nucleus of an atom, it has a relative mass of 1 and a relative charge of positive 1. Neutron has a relative mass of 1, however, it has no charge, so its relative charge is 0. When it comes to electrons, guys, its mass is so small, it's almost considered to be approximately 1 out of 2,000. So we can say that the electron has almost no mass at all. And it has a relative charge of -1. See, almost all the mass of an atom is situated inside the nucleus, because as we can see from this table that the electron has almost no mass at all. So the proton and the neutron makes up the total mass of an atom. Now, as you go down the group, starting from 1 to then 2, 3, 4, 5, 6, etc., with the increase in proton, the number of neutron increases almost in a consecutive or in a similar pattern. Nothing really changes much up until the 20th element. After that, things change almost dramatically. After that, every change or every increase in the number of protons causes a massive increase in the number of neutrons. For example, the element lead in the periodic table, which has a symbol of Pb, has 82 protons, and you might think that the number of neutrons is somewhere around 90 or 85 or maybe even 95. No, that's not the case. See, in case of a number of an element with an atomic or a proton number such as lead, the number of neutrons increases up to 125, making a lead atom very heavy. So, what did we learn here, guys? That when you go down a periodic table, 1, then 2, then 3, and up until 20, the number of proton increase in the number of proton does not cause any dramatic change in the increase in the number of neutrons. However, after the 20th, things completely change. When the proton number increases, the neutron number increases in a magnifying manner. So the atoms also get bigger and bigger and heavier. Now, so far, we discussed that the nucleus is where the protons and the neutrons are situated, and on the outside are where electrons revolve. Now, all the protons of an atom, that's the proton number. But the proton number of an atom is also known as the atomic number of an atom. What is the atomic number? If you look at a periodic table, and look at any element, for example. Say, let's pick one. Let's say carbon. If you see carbon in a periodic table, you'll see something like 12 and 6. So, in the periodic table, the letter or the letters are the symbol. And this 12 denotes a number and the 6 denotes another number. What are those numbers? See, 6 is the atomic number or the number of protons that is present in one atom of carbon. So, in one atom of carbon, in the nucleus, there are 6 protons. And what is 12 then? 12 is the mass number, which is the total number of protons and neutrons inside an atom of carbon. So, to sum up, in an atom, the number of protons and the number of neutrons together make up the mass number. And only the number of protons is what is known as the atomic number of that element. So, in a periodic table, you can observe any element with their mass number and their atomic number in the following manner. Say, if you were to take the element carbon in the periodic table, you would see something like this. The symbol of carbon, which is C, and 12, its mass number, and its atomic number, which is 6. And this is in the case of carbon. What happens when it is in the case of elements like sodium or magnesium? In every case, guys, you will see that in the periodic table, the elements are always arranged in a manner as such. This box represents the symbol of the element in question. And on top of the box, on this side, you will see the mass number. And at the bottom, you will see the atomic number. The symbol represents the name of the element, either in Greek or in Latin, and M represents the mass number of that element, which is the total number of the protons and neutrons, and A is the atomic number, which is the total number of protons in one atom of that element. So guys, at this part of the lecture, we are going to discuss about isotopes. What are isotopes? Sometimes, not all atoms of an element are the same. For example, in an element in the periodic table, let's say carbon, there are, as we know by now, 6 protons and 6 neutrons. As a result, it has a mass number of 12, which is what we can see in the periodic table. However, sometimes we find carbon that has a mass number that's not exactly 12, that is higher than 12, which looks like this. So, this carbon atom has a mass number that is 2 higher than this carbon atom. How did that happen? What is different in this carbon what is different in this carbon, that which is not present in this one? So see guys, the only thing that is different here, as you can see from both examples, the only thing is different is the mass number. And mass number, as we know by now, is a summation of the proton and neutron. So the atomic number in both these carbons are same. So we can safely say the only thing that is differing in these 2 carbon atoms is the number of neutrons they possess. So in any element, in any 2 atoms of the same element, if there is a difference, if that difference causes a change in the mass number, that is usually because they have 1 or more neutrons that is more than the normal or the usual atoms of that element. And such atoms of an element who has the same number of protons but different number of neutrons, those atoms are known as isotopes. So in this example right here, if we come back, this is the usual carbon atom. This is the carbon atom that we usually see in periodic table. This is what is the natural form of the carbon. But when this carbon atom, the nucleus of this carbon atom has 2 extra neutrons, it forms this carbon atom, which has a mass of 14 and an atomic number of 6 like before. So what difference is there? Say this is an isotope, but how is this different from, how is carbon 14 different from carbon 12? See, there isn't much difference between these two. There are no chemical differences, there are no stark changes in chemical reactions, not much really. But the only difference that may arise is they may have slightly changed physical properties. This is a bit more massive than this one, as you know, as you can see, because of the presence of extra neutrons. And so therefore, the thing that really differs between isotopes are the physical properties, the boiling point, the melting point as such. Examples of few other isotopes apart from carbon are maybe that of hydrogen and chlorine. See, hydrogen, if you look at it in the periodic table, hydrogen is an element with a symbol of H and 1. It has 1 proton in its nucleus and 1 electron. But hydrogen has isotopes which sometimes causes the appearance of hydrogen to look like this. Sorry, the first one would be like this, the number of protons, my bad. So this is an isotope of hydrogen. This is normal hydrogen, and this is an isotope of hydrogen. Another isotope of hydrogen looks like this. So guys, if you observe closely, what is the basic difference between these three? The number of protons are always the same. So the only thing that may be causing the difference between these three are the number of neutrons they have. See, this guy right here, if I single this guy here, and if I blow it up for you in here, so this is the diagram of a hydrogen atom, isotope of a hydrogen atom. Here you have the electron, this is the nucleus. In case of the usual hydrogen, we have only 1 proton. But see, there's the mass number, which is 2. So mass number as we know by now is the summation of proton and neutron. So along with 1 proton, what we have in here is an extra neutron with 0 charge. So the proton plus the neutron is making up the mass number of 2, thus causing the isotope of hydrogen, which is also known as deuterium. And in case of this guy, in this nucleus, along with 1 proton, see, because the atomic number is again the same, 1 proton, the only thing that is differing in here is the number of neutrons. So you see, here we have another neutron in case of this guy. I'm showing you the example in the same diagram because if I draw more and more diagrams, it may get a little bit confusing. So I hope you are able to understand what I'm trying to say, what I'm trying to make you understand. So if we move on our attention to right back here again, we see that in case of this guy, this isotope of hydrogen, the third isotope of hydrogen, the only thing that differs is that there are 2 neutrons that are not present in the original or the single hydrogen, of which these 2 are isotopes of. The neutrons aren't present in here, but here you have 1 neutron and in here you have 2 neutrons. And so therefore this guy becomes the isotope of hydrogen. And this here is known as tritium. So this isotope of hydrogen containing 1 proton and 1 neutron in its nucleus is known as deuterium. And this isotope of hydrogen containing 1 proton and 2 neutrons in its nucleus is known as tritium. Another example of isotope, a very marvelous example of isotope is chlorine. Let me show you how it's marvelous. So, if you search chlorine in the periodic table, you will come to group 7 and you will find chlorine who looks like this. Cl, which is the symbol of chlorine, and 17, that is the atomic number of chlorine, and 37.5, which is the mass number of chlorine. I know, weird, right? In decimal, a mass number that is in decimal points. None of the other elements has a mass number that is in decimal points. So what's the case with chlorine, right? See, this is the marvel of the isotopes of chlorine in here. Chlorine has 2 isotopes. So the 2 isotopes of chlorine are chlorine 35 and chlorine 37. And this happens because in chlorine 35, the nucleus has 17 protons and 18 neutrons. So, in one atom of chlorine 35, in the nucleus, you have 17 protons as always, and you have 18 neutrons. So when you sum them up, it forms a mass number of 35. That is one atom of chlorine 35. Now, in case of chlorine 20, what happens is, in case of chlorine 37, guys, what happens is, in here, you have 17 protons as usual. As I have said before, and we have learned, the number of protons really doesn't change. What changes is the number of neutrons. So what happens here is that in case of 37, you have 17 protons and 20 neutrons, thus forming the mass number of 37. So in 35, you have 17 protons, 18 neutrons, and in 37, you have 17 protons and 20 neutrons. For your ease of understanding, I will denote the things right here. 17p plus 18n. And in here, we have 17p plus 20n. Okay, so that still doesn't explain how 37.5 arises. See, it's very simple. The chlorine that we observe in the periodic table is an average of the number of atoms of both these isotopes. When you do that, you find one atom of 37.5 mass number and 17 atomic number chlorine that we see in the periodic table. So you see, isotopes are these unique atoms of elements that has one particle that varies in number. And as a result of this variation, their physical structure changes, even if by a little bit. There isn't much change in their chemical reaction. There isn't much change in the way they behave than one another. There is very slight changes in the physical properties. But other than that, there isn't much change between these things. So isotopes, if I am to repeat myself again, are atoms. Isotopes are atoms of the same element with different number of neutrons, but the same number of protons in the nucleus. Isotopes can be further divided into 2 types: radioactive isotopes and non-radioactive isotopes. Radioactive isotopes are isotopes that give out radiation. Radiation in large or small amounts can be harmful to the human body. And whoever is handling, workers or professionals or researchers that are handling those radioactive isotopes or radioactive particles has to be very careful. They have to wear specialized suits and they have to take extra precautions so that they are not harmed. It was radioactive isotopes that caused the massive pollution in the Chernobyl disaster in 1986. Guys, if you are still not acquainted with the Chernobyl disaster that took place in 1986, I suggest you Google it and learn about it right now and learn about the radioactive isotopes that cause the most damage. Now, most isotopes that are found in ground and in air are not radioactive. Radioactive isotopes are usually produced artificially in nuclear reactors. How they are produced and why radioactive isotopes are produced in the first place, that is, their advantages or disadvantages, is something that we will discuss right now. Radioactive isotopes have important uses. One such radioactive isotopes that is used in medical purposes is cobalt-60. Cobalt-60 has a symbol of CO, and so this is what a cobalt-60 looks like. And why do we use cobalt-60? So the intense radiation that is produced from one isotope of cobalt has the ability to kill the rapidly multiplying cancer cells. And as a result, it slows down the proliferation of cancer. And also, we use cobalt-60 to sterilize medical instruments. That is, the cobalt-60 efficiently kills all the bacteria and all the other disease-causing pathogens that may reside on those instruments. Because those instruments have to be perfectly sterile when they are used in a surgery or any medical use. So, cobalt-60 is a radioactive isotope that is used in chemotherapy of cancer, also for sterilizing medical equipment. Some other uses of radioactive isotopes are: radioactive isotopes in their nuclear reaction produces a large amount of heat energy, and that can be used to provide electrical energy. Now, that amount of electrical energy is always useful, so a small amount of radioactive isotope can be used to provide electrical energy to the most remote places of Earth. And then, radioactive isotopes are also important to provide energy to spacecraft that explores other planets that explores outer planets like Jupiter and Saturn. Also, another important use of radioactive isotope is that some people have irregular heartbeats, and those people need a special instrument to be implanted inside their chest. That instrument is known as a pacemaker. Now, the job of a pacemaker is to provide a little bit of an electric shock to the heart so that a steady heartbeat is ensued. Now, since it's an instrument that provides electrical shock it needs a battery to keep it running. When that battery is made up of radioactive isotopes, it can run for an amount of almost 20 years without any change. But in case of a normal battery, we might have had to change it every 10 years, which would have been problematic because each time you were to change the battery of a pacemaker, you have to cut open the chest of the patient, take it out, change the battery, which is a large risk and it's expensive. So if you use radioactive isotope instead on the pacemaker and you install it inside or implant it inside the chest of the patient, then it can run for almost 20 years or more. So guys, while learning about the advantages of radioactive isotopes, we learned that a radioactive isotope in its nuclear reaction will produce a lot of heat energy. And that heat energy can be used to provide electrical energy. But how does that happen? We need to know the detail or at least a brief reaction process that produces heat, which then produces electrical energy. This is something that we are now going to discuss under the topic nuclear energy. So let's dig in. Radioactive isotopes are used to provide large amount of energy by the process of nuclear fission. What is nuclear fission? Nuclear fission is something that you can see in this diagram. Nuclear fission is a reaction that is carefully conducted in a nuclear reactor. It is the artificial bombardment of a nucleus, in this case a uranium nucleus, which is also the fuel. It is the artificial bombardment of a uranium-235 nucleus with a neutron. 235 is the mass number of uranium. So what happens in here is that a uranium nucleus is shocked or bombarded with neutrons. Neutrons hits the uranium nucleus, and this causes an unstable formation or an instability in the nucleus of uranium-235. And as a result of this, the nucleus of uranium starts to divide. It's kind of like how a cell divides during cell division, during the process of cell division. So a nucleus kind of thins out in the middle and divides into two different atoms of two different elements. As you can see here, that after the fission, which is the division of one uranium nucleus or of one uranium nucleus, two further different atoms of two different elements are produced, kryptonium and barium. And also this produces a massive amount of energy and more neutrons. So this neutron, in the beginning, we start voluntarily. We do it by ourselves. But after the fission reaction ensues, the process itself produces many more neutrons. And these neutrons further attacks more nucleus of uranium-235, causing this entire process to go over and over again, and therefore causing a production of a lot of heat energy. Now this thing where the process repeats itself over and over again is what is known as a chain reaction. So in a chain reaction, we always begin with one neutron or a voluntary bombardment of neutron in a nuclear reactor, which hits an uranium nucleus, causing it to divide and produce more neutrons, which causes division of more uranium nucleus. And as a result, the amount of heat energy is used to further produce more electrical energy. So a lot of heat energy is produced at the end of these fission reactions. That heat energy is used to produce steam, and that steam is used to drive a turbine and a dynamo, which then produces electrical energy. That electrical energy is useful for our houses, our industries, and also they can be transferred to the remote villages which does not have electricity at all. Now, these nuclear fission reactions that we conduct in nuclear reactor, they're controlled. They are conducted in a safe or almost safe environment because there is no 100% safety in any scientific experiments, as you know. So they are conducted in controlled environments. But when a nuclear explosion occurs in weapons or in bombs, grenades during wars, that is deliberately produced by adding uncontrolled or an extra amount of these radioactive elements. Say, for example, in a nuclear weapon that is to produce an explosion, we add about 10 kilograms of uranium-235 or plutonium, so as to produce an uncontrollable amount of nuclear fission reaction. This fission reaction will cause a set of chain reaction so intense, so big that that explosion cannot be controlled, and that causes a production of a lot of heat energy and this massive exploding circumstance that harms human lives, human structures, homes, everywhere. So nuclear elements or nuclear radioactive isotopes, as they can be important, they can also be really, really harmful. See, even though we are conducting all these experiments in a controlled environment, guys, it still can end up in a massive disaster. As I said, that happened in the Chernobyl disaster in 1986. So, for example, if we were to have a nuclear reactor in our midst that works and provides important energy, heat energy, electrical energy that are necessary to us, but this is also so harmful, any accident can cause a disaster so big that it can harm our generation and the next. Do we really want such a thing, such a helpful enemy in our midst? So see, guys, nuclear isotopes or radioactive isotopes, as much as they can be helpful in several uses, in several medical and other uses, they also possess a lot of threats. So guys, this was the end of part 2 of atomic structure and the periodic table. I hope I was able to help you understand everything that I have explained in this chapter and on the previous one. In part 3, we will delve deeper into the atomic structure. We will look into the arrangement of electrons and electronic structures, and we will also discuss about the periodic table. So, until the next part comes along, have a nice day.